All right, good morning. And in today's video, we're going to be looking at the analysis of a squirt gun. And using Bernoulli's projectile motion, we can get an idea of how far a squirt gun will shoot. And then I'm going to derive the equations and then create a programming code that will plot x. So how far in the x direction the water will shoot as a function of pressure inside the squirt gun. All right, let's get started. So first, given. Let me zoom in a little bit more. We got rho, which is 1,000 kilograms per meter cubed because we're dealing with water. We're going to need gravity, 9.81 meters per second squared. Our H naught, or sorry, our H or Y naught initial, we're going to go up 0.86 meters. The gauge pressure in the squirt gun, we're going to go from 0 to 20 psi. And then we're going to have 0 degree and 25 degrees. So let's make a sketch. Let's do black. Okay, so here's the squirt gun, rough idea. All right. And then we have water shooting out, and then it falls. Okay? So let's put some coordinates on here. Put some water in here. This is state 1, state 2, and then when it hits the ground, we'll call state 3. This is Y naught, and from this position over to the ground, we'll call X. Okay? The last thing we need is right here. Put a datum here. Oh, actually, you know what? Let's move that to here. Just because I like to keep state 2 if it's below. I like to keep the bottom part there. Okay, so from state 1 to 2, we have Bernoulli's, and we'll talk about that. And then from 2 to 3, we'll do projectile motion. All right. All right. Find. We're going to find X versus P1 gauge. Okay. Let me put some assumptions right here. So minimum or pretty much no friction or air drag. And we're going to treat the water as like a projectile going out of the squirt gun. Okay? Steady flow. And incompressible. Now again, these are like we're treating this like it's going to continuously flow out of that squirt gun until it empties. Okay, but we're going to consider that as a continuous thing. And we're going to neglect the elevation change of changes from 1 to 2. And we're going to assume V1 is small compared to V2. So V2 is the velocity of the water coming out of the squirt gun. Why do we do these assumptions? Because those assumptions, you can use Bernoulli's and you can use projectile motion, because if there's no air drag, we can just assume the only thing being affected by the water is gravity. Okay. So let's get to the solution. we have Bernoulli's from 1 to 2. And if you remember, Bernoulli's equation is P1 gauge over rho plus V1 squared over 2 plus GZ1 equals P2 over gauge, P2 gauge over rho plus V2 squared over 2 plus GZ2. Cool. All right, we can cancel a bunch of stuff. We neglected elevation changes. This is gauge pressure, so the gauge pressure shooting out at point 2 is 0 because it's atmospheric. And this velocity we assumed is 0. So what we end up getting is P1 gauge over rho equals V2 squared over 2. And we can solve for this V2 velocity assuming we know the gauge pressure. And we can. Cool. All right, let's keep going. So now we have an equation for V2. Now let's use projectile motion from 2 to 3 to figure out how far this thing is going to go. Let's use projectile motion. We have x direction and we have y direction equations. We know that ax is 0, vx is v naught x, and x equals x naught plus vox t. In the y direction, we know it's negative g. We know vy is v naught y minus gt. And we know that y equals y naught plus voy t minus 1/2 gt squared. All right, I'm going to call equation 1, 2, 3, 4, 5, and 6. And I'm going to cancel this x naught because we're starting x naught right at point 2. Okay, so we can put 2 to 3. All right, so from equation 3, x equals x equals v2 cosine theta t. Okay, because if we're at an angle, this is again right at the this is point 2. We could have this come at an angle, so we could have v naught x, and let me do orange, v naught y, and we're assuming that these are just v2, let me do that in purple, v2 cosine theta and v2 sine theta. Okay, so I'm putting the angles in to have a complete analysis. Now what I'm going to do is I'm going to solve for t and plug that into the y equation. So we get x over v2 cosine theta. All right, so next, from equation 6, y equals y naught plus v2 sine theta minus 1/2 gt squared. I'm going to plug in t into this equation from above, okay? So let me do that. And I'm going to also, this is 0 because the final y should be 0, okay? It's hitting the ground. So we got 0 equals y naught plus v2. Oh, I forgot, sorry. This is times t, right? Minus 1/2 gt squared. I hope you caught that. So v2 sine theta times x over v2 cosine theta minus 1/2 g And then this is x over v2 cosine theta all squared. Ooh, cool. We're getting somewhere. Now, we look, these two cancel, sine over cosine is tan. So we get tan theta times x minus 1/2 g. I'm going to rewrite this as x squared all over v2 cosine theta squared. All right. Okay, now let's plug in v2. Oh, sorry. Plug in v2. That was from Bernoulli's. And let me put x in front. Minus 1/2. And let me rearrange this. So g x squared over 2. And then this is going to be the square root of 2p1 gauge over rho. But this is squared because this is v2 right now, because it's v2 squared. And then this is cosine theta squared. Okay, I kind of plugged in v2 and then kind of took the square. Okay, now the square root of a square, you just get the same thing. So let me write this one more time. We get x plus x tan theta minus g x squared over 2 times 2p1 gauge over rho times cosine theta squared. All right. Okay. All right. One more time. Let me do this in green. Make it look a little bit easier to read. Minus x squared, and we got a g over times rho over 4 p1 gauge cosine theta squared. I just kind of rearranged that equation. Why? Because look, we have x squared, and a constant. That is the quadratic equation, which I'm going to rewrite like this. Where we can solve it, plus or negative b plus or minus square root b squared minus 4ac all over 2a, where a is c1, b is negative tan theta, and c is negative y naught. So we need to use this quadratic formula to solve the quadratic for x for each pressure. Okay, so we're going to solve for x for different p1g values, but you have to use the quadratic equation because it's quadratic. Now, just a cool little note. Let's say theta equals 0. Well, this equation becomes a lot easier because the tan of 0 is 0. Cosine of theta is 1. So you get 0 equals y naught plus 0 minus x squared g rho over 4p1 gauge. And you can solve for x directly by just the square root of 4 y naught p1 gauge over g rho. So if it wasn't at an angle, this becomes a lot easier because you don't have a quadratic equation to solve. But, so we're going to use pretty much this equation by using the quadratic formula for different thetas and gauge pressures. All right, so let's take a look. I did that already. So let's take a look at the code. So let me bring it over here. And let me make this a little bit bigger. Okay. All right. So here's my header at the top. Straightforward. CLC, clear all. And let's look at the givens. So I first like to do 1 theta, so 0 degrees, and 1 pressure, and get the formulas. And then I can work around how I can do this with loops, okay, with multiple thetas and multiple gauge pressures, okay? So theta is 0, boom. Why not? 0.86, and then I'm using 10 psi. I'm just converting that to Pascal, remember. Then I put properties, water properties, and gravity. So density of water, 1,000 kilograms per meter cubed. G is 9.81 meters per second square. Now, so like I said, A is C1. That's G times rho over 4 times P1 gauge times cosine D theta. Remember, D you need for degrees because we're doing degrees, not radians. And you don't need to put the dots here, but I did. You don't have to, okay? I just know that P1 gauge is going to be a matrix. It could be, and so I just put those in there. Then I said, okay, here's my quadratic A, B, and C. And then I actually built a function code for quadratic. So if I put these as my inputs, this is my function code called quadratic. I'll get 2 answers. And I can determine if one is negative or positive. Okay? I'm just putting my computer back for a second. There we go. So I can end up typing. Now, if I jump over, here is my quadratic function code. So remember how to make function codes. You just type function. Here is our outputs, which are on the left of the equal sign, equals function name, and then here's our inputs, which are on the right side of the equal sign. So again, I just did plus or minus, negative b plus or minus square root of b squared minus 4ac over 2a, and then I had 2 answers. Okay. So if I go back, when I run this, oh, sorry, I jumped the gun. Let me type return and show you. So if I type answer 1 and then answer 2, one's positive and one's negative. And then I can change the pressures, the angles. So here's 25, just to make sure that it's giving me a reasonable value. So answer 1, answer 2. Okay, that makes sense. Answer 1 should be larger. This because you're shooting at 25 degrees, it should go farther, than 0 degrees. So I always write this, I always do my code this way, and then I'm like, well, I want to plot, but I want it for multiple angles, probably, and for multiple gauge pressures. So let me go down here. So let me start right there. Cool. So I'm just writing a new code. Again, you don't have to do this. You can just do this code. Here is my theta, and I can have multiple degrees. I just did 2. Why not? And then here is my gauge pressure from 0.1 to 20, because if you do 0, you'll get not a number. And again, converted it to Pascal. And then style, you're going to notice that I'm going to plot 2 lines, one for this angle and one for that angle, so I have black and red. So say you put in 45, then you would have to put in, let's do magenta. You'd have to add that other line. Okay? I'm just going to do 2 for right now because it's easy to see. Properties, again, rho, G, nothing new. Now, because you have 2 different matrices, you're going to need 2 different for loops. You're going to need a nested for loop, okay? Because you need to calculate X for each pressure in the quadratic, okay? So you have to put in those single numbers. You can't do a whole matrix at once. It gets tricky. It just won't work. It's too hard. So that's why you have a nested loop. My outside loop is theta. All right. I always like to do, okay, these are the two angles that I'm looking at. That's like the first for loop. And then inside is going to be, okay, I'm going to calculate my x for those particular pressures for that specific angle. So let me scroll down here. So again, it's the same equations from above. Same exact equations. You just copy and paste. However, you see here I have for I equals 1 length of P1. That's going to do the loop that many times. Wherever I have P1 gauge, that's where I need parenthesis I. Okay. Wherever I have theta, TH, you need parenthesis J. Okay, so parenthesis J there, parenthesis J there. And then boom, I find my quadratic. I check to see if they're greater than 0. If it's not, then it's answer 2. And then I actually clear everything, and then it goes up, back up here. Okay, so this loop right here, that calculates X for each pressure based on 0 degrees first. And once it's done all the pressures, okay, then it will plot, okay, and then it goes back up to the top here and does the next theta and does the whole thing again, okay. So the way I stored X is a matrix. So this is your row and this is your column. So the first entire row is going to be your first theta, which is 0. And then these numbers are your pressures, okay, your columns. Okay, and then when you get to your second, this second row would be for 25 degrees. And I'll show you here, okay. So, let's see, we plot P1 gauge. I wanted to plot it in PSI, and then I'm plotting the first row, okay, or the rows of axes. These are my styles. That's that black or red, and then I did line width of 2. And I'm holding on, and I do a grid, okay? So let me run it and show you. I'll just type return there. Now again, my Surface Pro is kind of small, but you have down here PSI. Up here is your X, and then these lines indicate your theta. Okay, so 0, 25, and it's black and red. Now, you want to see the matrix, so X. So you see how there is, let's see, how many, 200 columns. So each column represents your pressure with your, if I scroll up here, 0.1 is the first column, and the last column, 200, is 20. Each row, the top rows, correspond to an angle of 0, and then the bottom rows correspond to an angle of 25. So let me just change it to, let's do by ones, just to show you. And let me clear, and let me type in what I say, X. Okay, it's a little easier to see because there's only 20. So the first row, this is the top line here. Okay, so if I did X1 colon, that means I can grab the first row, and that's the top lines. Okay, that is the angle for 0. So say we wanted another angle. Let's do 45. Let's do magenta. And the legend is not going to work, but I can fix it. I hope that's right. I didn't check that, actually. Oh, don't need that. XPY. Let's see if it works. Yep. So legend \theta will actually give you a theta symbol. Okay, 0, 25. So I have 1, 2, 3 lines. That's why I needed 3 of these in single quotes, and then I just put labels on. Okay, so the black is 0, the red is 25, and then the magenta is 45. And again, if I go to my other screen, it looks so much better. My Surface screen, for some reason, is small, but it should be okay on your computer. So, I would take a look at the derivation, take a look at this code, create your own, and if you have questions, let me know. Good luck, and you should try this at home with a squirt gun and see if you can match the experimental data with theory. 0 degrees works pretty well. When you get to higher angles, sometimes it doesn't work as well. You get a lot of your percent air increases because of friction and air. If you have any air distribution, any air disturbances, it might mess it up. But it's a pretty close approximation. All right, have fun and take care, and thank you for listening.